All right, so welcome to the last class of our programming. Today, again, is a bit of a kind of survey of many different things. Not too much, there's no breakout rooms or anything, so not a lot of interaction, but if you have any questions, definitely stop me and I'll try and add some feedback if there are parts that you're more interested in than others. But today, just to go over muddy points from last class on the website, there were kind of two main questions, mostly related to ANOVA or the ROC curves part, which totally makes sense because those are very complex statistical topics. For ANOVA, all I really wanted to say is that there are many ways to do ANOVA in R. They basically all do the same thing. I showed you two different ways, mainly because I have heard that AOV is used in biostats classes, whereas I tend to like to use capital A ANOVA. And it all has to do with what kind of ANOVA you want to run in terms of, is it a one factor, two factor? Are there an interaction term? And so because that really affects what tests you want to run. So if you want to learn more about type 1 versus type 3 sums of squares, which is the main difference between these two functions that you can change your sums of squares output. I put a couple links here and also in Slack for you to learn a bit more about ANOVA. But also just a plug for the experimental design class that's in biostats. Park teaches that every other year. So I think next year he'll be teaching that, and I think it's in the spring. But that's where you learn all about ANOVA and experimental design and all that related stuff. So just so you know. And then ROC curves. ROC curves is, I would say, takes a while to really fully grasp it. My PhD dissertation was very much related to prediction methods, and I remember being very confused by ROC curves for a long time until someone explained it to me in like very simple language. And so I found actually a video that kind of does that. It's pretty silly. It even starts with a silly song, but if you get past that, there is some good explanations about how you build an ROC curve based on thresholding. Nice visualizations and stuff. So if you have 20 minutes and you want to learn more about it, that's pretty good. But there is a whole textbook that's really great about classification and prediction. So you just Google it. It's not free online. You actually have to buy it, but it is a really good textbook if you're interested in learning about prediction methods. And there was also a question about how do you select a cutoff value. That again is a long explanation and can be done many different ways. If you're interested, you can read this. I put it also in Slack. There are just many different ways. A lot of times it's based on sensitivity or specificity or maximizing your prediction accuracy in some way. But there are many, many, many ways. So if you're interested in learning about prediction, I don't know if there's really a good class at OHSU. There's the machine learning class in the biostat group that Dungsuk teaches every other year, I think. And then the DMICE, the Department of Medical Informatics group, also teaches some machine learning methods. And so I'm sure they talk about classification and prediction accuracy in those classes. So that's another way to learn more. I just realized I lost my chat, so hopefully you're not talking to me. Go. There it is. Okay, silence. Good. So I think that both those topics are just, it takes time to learn about them, and I really didn't do them justice. So I encourage you to read up about that. They are both interesting things. I use prediction accuracy a lot in my work, and so I think it's a good thing to learn. There also was a question, I regret not talking more about R Markdown in this class because it is a nice thing to get used to customizing and using to your advantage. I mean, we've used it as a tool to produce analysis reports, but we haven't really talked about how to make those reports look great. And so I'll talk about it a little bit today in terms of like, what are you putting in your markdown and how do you make the HTML or whatever you're knitting to look good. Just a little, very brief if we get to part 10 today. But my one tip, I think, is if you're giving your HTML file to someone, like putting it out as a publication or like as a supplement to your publication maybe, or like to your collaborator, is to try to never print out regular R output. So for instance, if you have a table you're trying to show, use all those helper functions that I showed you, like GT, to make a nice table, or cable, which I didn't really talk about, but it does similar things. And don't print out like the default R model output. That's useful to me as a statistician, but someone who doesn't care about all that extra information is just going to glaze over it. And it just isn't conveying the output in a nice way. So that's why I showed you like GT summary tables. There's another package, Final Fit, that does similar things. So I think that is my main recommendation. Don't worry too much about what the raw output is looking like in your HTML, because you just don't show it. Like clean it up to make it look nicer. And that takes extra time, but I think it's worth it if you're sharing your report at all to anyone. So just kind of a simple way to fix things up. And there's also another package, which I'll show today in part 10, called DT, which it didn't work. I don't know why it didn't work on the website, but I'll show you it in an HTML file. And that's kind of like GT, but it actually makes an interactive table in a markdown document, the knitted markdown document. So you can like search it and filter and stuff. So I'll show you that. And I'll talk about this in a minute when we get to part 10. And then, so for machine learning, there's also was a comment that they wished I had time to talk about machine learning, and so do I. I had so many things I wanted to cover, but we ran out of time, of course. But I will say that last year, Ted, who taught this class, spent 2 whole classes on tidy models and machine learning and prediction, even classification and stuff. When I talked to him, he recommended that I spend more time on data cleaning and kind of the stuff at the beginning, which I did, but that meant that we ran out of time to talk about this stuff. But having those resources is really useful. You can watch his classes here at his links. And there are a lot of books and workshops on this. There are chapters in the R for Data Science textbook that's online that talk about modeling, but then in terms of what we call tidy models, which is a package in the tidyverse, tidy modeling is slightly different syntax than what I've shown you. I've shown you the very kind of like base R statistical models, like simple stats models that we all see in our stats classes, and like t-test, linear regression, stuff like that. But if you want to do more what we call machine learning, which is they're really just more advanced statistical models, tidy modeling, it makes it a little bit easier to do all of those different models. And so here's some resources if you want to learn more. There's a lot out there. And so thanks for all of your nice messages about how this class was helpful. I am glad. And I really think that like we've really just touched on some basic things. And for some of you that may have been not enough and you wish you learned more. But I think once you get to this point, it's not going to be hard for you to just keep learning, because you kind of just have to get over that first hump. And there's so much out there to learn from. I think that you have the tools now. And last note is, if you do get I know I've asked you for a lot of surveys and feedback and stuff, but if you do get the like end of the quarter survey link from OHSU and you have a chance to fill that out, that'd be really helpful, just so like people actually that are in charge of making classes, that they know that this class should keep happening, because right now it's just like a topics class, and they need to understand that it's not, it should be regular. It should be a regular class. So we'll see. So that's all I have to say. Please, yes, I know. And we've also talked about like this, it's a biostats class. When Ted was here, he left, which is why I'm here by myself. We talked about teaching it together and making it like a conj course. So it could be across all different departments. But that turns out to be quite complicated. So we'll see. We'll see what happens. I also wish it were in the fall, but I don't know if that's possible. Yeah, and so there's a comment that the epi people should take it. Yeah, I agree. I don't know why. I don't know why it's so hard to publicize courses, but yeah, I think I definitely agree. It's useful. All right, so I didn't finish part 9 last time. Let me see. I had some notes to myself to make sure I didn't forget some things. Okay, yeah, there's a reminder to give you a break. So if I don't remember, tell me. All right, so this is where I left off, I think, in the correlation section of part 9. This is, so this is what I'm doing. I'm restarting R just to make sure I was running some stuff in here. So to clean my environment, and then I'm gonna run everything up to this point, which I do by clicking this little side arrow or whatever that is, play button. And so up until now, we've talked about fitting models, but there, of course, is kind of a very simple statistic that we often calculate called correlation. And there are several different types of correlation, but usually what we're looking at is the linear correlation between two continuous variables. So that's just simply Pearson's correlation. And there's actually a nice package that's been around a while called tidyeval. I don't know why it's called that, but they have a GG pairs function, and you use it on a data frame of variables where you want to get a sense of how are all those variables correlated. You can change which correlation it shows, and you can change a lot of different custom things about it. But I do just want to show you like the default usage. So here I'm back to using the PIMA diabetes data set, and I've selected 6 variables that I just want to look at. And so everything is still running. We did a lot last time, apparently. It's taking forever. Let's see what happens if I run this. There we go. Nope. Probably shouldn't have run it all. Yeah, no. Any questions? Oh, someone mentioned that the epi friends have been watching our videos. That's kind of exciting. That's good to know. Well, anyway, when this is done eventually, which my poor computer is really taking a beating here, I think it's going to show us something that has both correlation and distribution of the data. And it's going to be a lot of information, but I think it's one of those things like skim, yeah, mostly skim, where you're just kind of interested in looking at what your data looks like. Is it skewed? Are there like some really strong correlations? It also helps you see if there are kind of anomalies or issues with the data that you should really like pay attention to. I'm gonna see if I can just stop this. Okay, let's try that. You get a lot of different warnings from this one, which is just talking about all the missing data values. But this is the default. It's not beautiful, but you get the correlation for each pair. So you have glucose, pressure, et cetera. And then so you look along the row and the column. So for like glucose versus blood pressure, the correlation is 0.22, not very big, but something. And so then you can see the scatter plot of those two and also the distributions. So you get a sense of skewness and like, what is this? This is that, if you remember, we had a column called pedigree, which is essentially a function of family history of having diabetes. And so you get a sense that's very skewed. And then you also come pick out like the most correlated variables. So what is this? Tricep thickness and BMI are very correlated. That makes sense. Insulin and glucose are pretty correlated. Also makes sense. So I like this one. And you can make it look nicer if you actually want to show someone this figure. You can make a grouping color. So this is GG pairs. Inside that GG pairs function, you set a aesthetic where you map color to diabetes. And here alpha is like the opacity of those dots. It's kind of nice to set an alpha that's lower than 1 for something where you have a lot of points piled up on top of each other, because if you look at these black dots, it's just a black blob. You can't really see the kind of how many points are there. And even still now, it's still hard to see. So we really need a bigger picture, but if this works, it's kind of a quick thing. And you can see the color is now by, what I do, diabetes, which is our outcome. You get a distribution of each, you get kind of a count, which is like a bar plot of the counts of diabetes. You get a lot of information. I would make this bigger so I could see it better, but you get correlation within diabetes and across both categories. It's really nice to be able to see all that information. There's also a really nice vignette, I guess you'd call it. This is, there's a version of this here and also in the, I think it's in the Palmer Penguins package website is a version of this. It's talking about how to run PCA on this data. So PCA, principal component analysis, is technically, I mean, people call that machine learning and statistical learning and big data learning and statistical models, whatever, you can call it whatever you want, they're models. PCA is an unsupervised machine learning method, which means you don't take into account any outcome, you just try to cluster your data. And so you can see this is a really good, if you don't know much about PCA, I would look at that. It's a nice explanation. And so from there, she ran this same GG pairs example. And that's because it's interesting to see the different species and how they lay out on the plots and in terms of those continuous measurements of the penguins. And so you can see how they cluster together and which of these predictors or measures are best at grouping together your species. So you can see like bill length versus flipper length. Those species do separate out pretty well. You get a clear idea of which one's which. So that gives me an idea that those are pretty strong predictors of species. Whereas maybe bill depth and flipper length don't give you enough information to separate out Adelaide versus chin strap. So you can learn a lot from a plot like this. And it's a nice thing if you have a lot of continuous measurements. And then another kind of more simple plot that I've actually seen people use in publications, because it is making quite an effective way of summarizing correlation. So here, I've just pulled out the numeric data. So this is pregnant to age. I've used this in passing. I don't know if I've talked too much about it, but if you put a colon in between a column and another column, it's taking everything in between those two. So it's like a shortcut of saying pregnant, glucose, pressure, triceps, insulin, blah, 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 all the way to age. So I've just selected those. And the correlation here is in the package core plot with the same name of the function, core plot. And in order to use this, I need to make a correlation matrix, which is what that argument is of that function. And the way I do that is just to use the core function that's in just regular R pack. It's like built-in R. And I take my numeric data. Here, I'm actually telling it to use Spearman correlation. So the rank-based, non-parametric more, not Pearson's, but Spearman's. And here inside of correlation is kind of it's an odd default. The default is to use every row, but that means if you have missing data, it's just going to give you a bunch of NAs. And so instead, I use the argument pairwise complete obs, which means all the complete observations for every pair. So for example, like pressure and triceps, it would throw out this row because it's missing one in triceps. It would throw out this row because it's missing in both, and this row, and it would calculate correlation on whatever's left. And so that I think is a good option to use there. So just to show you, I'll run the correlation and what that looks like. It's a very simple cross table and it shows the correlations, glucose versus pregnant, pressure versus pregnant, etc. One's on the diagonal because pregnant is correlated 100% with itself, and so on. This is a typical like correlation matrix. It's symmetric. And that is what I feed into the core plot function. And so what that turns into is, this is the default core plot. It makes like a visualization of that matrix, basically. The bigger the circle and the darker the circle is, the bigger the correlation. So of course, along the diagonal, again, we see those ones. And then we get it really points out to you the highest correlated variable. So obviously, number of pregnancies and age is highly correlated, because the older you are, the more likely that you will have had more pregnancies. And then something like insulin versus glucose is highly correlated. And there are a lot of ways to customize this. So one thing to note here is there's not really any negatively correlated data. Pedigree and pregnant are, you can barely see it. It's very slightly a red color, but everything else is blue, which means it's positively correlated. So another kind of customization on core plot that I like to use is to use method equals ellipse, which turns these circles into an ellipse, as you'll see. And I also selected type equals upper, because I don't really need to see the rest. It's a symmetric matrix. So what's on this diagonal is the same as what's on this diagonal, the upper versus the lower. And then the ellipses, instead of the size of the circle, it turns it into the flattening, I guess, of the circle. So something that is more elliptic, flat, has higher correlation. And so you can see, I like it because you can see the other circles a little easier, but now we get a sense again that triceps and BMI are correlated, etc. And you can even go wild and add in a bunch of other stuff. There's ways to add in distributions and all kinds of things. If you actually want the actual numbers of correlation, so 0.69, 0.66, 0.61, those were the highest ones, you can put that in the lower triangle. So there's a whole vignette about this. It's a nice kind of clean looking way to summarize your correlation within a data set. And this also becomes really important when you're doing machine learning or high dimensional learning, because you're probably going to have a lot of correlated data, and that can really affect your results and your estimates and everything. So looking at how correlated your data is actually really important when you have a lot of predictors. All right. Okay, so that was correlation. Switching gears majorly now to another very simple test that is often computed. We have chi-square test, which I'm sure most of you have used, especially if you're in categorical data class. And then it's kind of small sample size friend, the Fisher's exact test. So what we do here is we have two categorical variables. So up here, we had two continuous variables, and we were looking at that association through either the, say, linear regression is one way, or correlation is another way. So how correlated are two continuous variables? But if you have two categorical variables, usually you're looking at a chi-square test or Fisher's exact test. So in this data, let's suppose that we want to test the null hypothesis that pregnancy, and just make it binary, ever versus never, is independent of diabetes status, which is also binary, positive versus negative. And the alternative hypothesis, which is like our scientific hypothesis we expect to see or hope to see perhaps, is that pregnancy is associated with diabetes status. Is associated is kind of a general term, but that's what we think of when we think of a chi-squared test, independence versus not independent. And so in R, how we do that is with the chi-square dot test function. And again, this is another example of kind of an odd R quirk, that it takes in a totally different argument than we've seen before. So linear regression, logistic regression, we saw that you give it a formula. T-test, we saw you could give it a formula or two vectors. Chi-square test, you have to give it a table. And so either a 2x2 table in this case, or you could even, if you have bigger categories like the 3x5 table or something, whatever it is, it needs to be a table. And so what that looks like is we've in this class used table with a Y, and you can do that. But there's also the base R table. So I'm just showing you this in case you see some chi-square test example. I think this is probably the more common way to do it, is to use table of the two variables you want. So this is diabetes, this is pregnant ever. I've just pulled them from the original data set with a $sign. So you get those two vectors. And so you get this 2x2 table. And so from a 2x2 table, that's how you calculate like the odds ratio or the chi-squared test statistic. And you can also, like I said, table with a Y from janitor also works. You get the same 2x2 table. And so because someone has actually adapted this chi-squared test to work with table, that's the way I want to show you. And so we have our diabetes data, we create our table, and then we can pipe on the chi-squared test. And so let's run that. And we end up with, this is the printed, like the default printed output. Chi-squared is very small. Degree of freedom is 1. It's 2x2 table. P-value is very high. So this test, if we're using 0.05 as well, probably any p-value cutoff, but if we're using the p-value cutoff of 0.05, this is definitely not significant. So that means that we can't reject the null hypothesis. But if, let's say we wanted to create another binary variable such as insulin high. So here I've created a 0, 1 variable that is 1 when insulin is greater than 125 and 0 when it's less than 125 or less than or equal to, just so I can have another 2x2 table that I want to look at. Here we do have a lot of missing data in insulin, which we looked at for last class in our missing data section. But we can see that there is a 2x2 table. One thing to note though, is that missingness can cause some issues with our categorical analysis, because now it looks like we have 3 categories. And that may actually be a test you want to do, whether thinking of insulin high as actually a 3 categorical variable, 0, 1, NA. That may be the test you want to run, but probably you want to look at the complete data and run the test of whether 0, 1 insulin high is associated with diabetes, yes, no. And so what I do here is I actually drop the NA. And so I'm showing you here before I drop the NA and then after I drop the NA. And I've dropped NA for insulin high, which means I've filtered out all of the missing values of insulin high. And so you can see you do get a different test. So this is the first one before I dropped NA, and it has a degree of freedom 2 because I had a 3 categorical variable. Whereas if I dropped that missing category, now I have a degree of freedom 1 test because I have 2 categories for each of my variables. But it's so significant, it doesn't even really matter. P-value is extremely small. So of course, if you have high insulin, that's going to be a very strong predictor of your diabetes status. That's just how we diagnose diabetes. So this makes a lot of sense. So just kind of a simple output, but as we've learned so far, tidy, the broom tidy function will clean that up for us. And so that's why kind of what I was saying earlier, clean up your output. Like you can show this in your HTML, and you can actually see what it looks like. Let's see. Like this kind of output just doesn't look very nice. Like this. That's what it looks like in your HTML. You get all these comment pound signs, and you get, it's fine, you can read it. But what I would do is actually clean that up. And so, whoops, where'd it go? So I would run broom tidy on that output, which tidies up the, like you'll get the statistic and the p-value, and then I tack on GT just to make a nice HTML table here. So you can see it's kind of squished because of my tiny window, but you end up with a statistic and somewhere statistic, p-value, and it tells you the method, and the parameters is your degree of freedom. So very significant test. That's nice. And so the side note is is kind of what my point here. It does make a difference in table when you use table with a Y, whether you have missing values. But if you use table without a Y, with just the regular table, it doesn't show the NAs by default. So if we look at that, there's no NA column, even though I know there's missing values there. But if I run the chi-square test on that, I end up with the second one that I had up above, which was when I removed missing values. So just be careful when you have missing data, and depending on whether you use table with a Y or table without a Y, look at the table first, basically, and see if there's missing data showing up in there. And this is just a side note that the chi-squared output shows this, the chi-squared test statistic with degrees of freedom, which is the number of rows minus 1 times the number of columns minus 1. And so when you have a 2 by 2 table, you have 1 by 1 equals 1 degree of freedom. But if you have small numbers, small counts in your chi-squared table, it's generally recommended to use the Fisher's exact test, because it uses the exact distribution of your data, basically, of all the combinations of your data to run an exact test. If you want to learn more, take my class next spring when we talk about the theory behind that. But it is a exact test, which means that it is going to be like valid for small samples, essentially, and valid for big samples. It wasn't used as much because it used to take a long time to run. But now that we have modern computing power, it really doesn't matter. You could use Fisher's exact test for either one, big data, small data, whatever. And what it does is it's basically similar to a chi-squared test. It takes the table. So this is, again, is my data. I dropped the NA, I did the table, 2 by 2 table, and then I say Fisher.test is the name of the function. And then I, again, just tidy it up. And you get the same kind of output. You get the statistic, p-value. Fisher's exact test actually gives you the odds ratio and the low and high confidence limits for the confidence interval, which is something that is nice. So you end up with a little bit more information from a Fisher's exact test. And it tells you a method, 2-sided test. You can also do a 1-sided Fisher's exact test. So, any questions so far? Scrolling problems. My last point on this, which I just did briefly, that point is that you don't always need a 2 by 2 table. You can do what we call R by C tables, which means however many categories you have. Here I've made a different categorical variable, which is the insulin cut up into 3 tertiles. So I use the n-tile function, which we've seen. I think someone did the function of the week on that. And I told it I want 3 buckets, I guess, 3 categories, which puts it into the 0 to 33%, 33 to 66%, 66 to 100% buckets. And so that means this is a 3 categorical variable plus the missing values. So I remove the missing values. And if we look at that table, you can see in negative patients that we have 118, 83, 63 in the tertiles. So the tertiles are created over the whole population. And once we divide it up into diabetes negative and positive patients, we can see the side distribution change. They're not equal in every bucket right now. We see a rising number going up to higher tertiles in positive diabetes patients, and then the number gets lower in diabetes negative patients, which means it looks like there's an association. And if we run that test, chi-squared test here for a 3 by 2 table, we have a 2 degree freedom test, and we still have a very significant p-value. So that means that insulin, even when categorized into tertiles, is associated with diabetes status. All right. Okay, so the next one is going to be very strange to anyone who has never worked with survival data, which I kind of think is most of you, probably. I don't think anyone's taken the survival class. Okay, well, just bear with me. This will come very useful if you do take survival class. So survival data is actually strangely something that only biostatisticians tend to work with. If you go to a stats program, they don't usually have survival analysis class. I think that's one of the big differences in between programs. Depends on the program, but and I think, I mean, I know it shows up in other situations, but I think it's more common in biostatistics because we are often looking at follow-up time in a study, or time to death, or time to being diagnosed with some cancer, or time to recurrence. But it's also used in other situations like, I don't know, time to anything really. It's any time you have data where you're following people with different numbers of days or years or whatever, different lengths of time. So if you looked at the smoking data that we've used before, there's actually a column somewhere, days to last follow-up. So what this, I don't exactly remember the structure of this data, but it's the tumor data. And we have various information about the samples that people gave. And I think what it's sampling is tumor samples. And then there's a sense that you have an outcome. In this case, we're thinking of vital status, alive or dead, and days to last follow-up varies with each person. And so if we assume that what this data is meant to be is that the sample was taken at day 0, and then the third person, say, was followed for 2,099 days. And at that point, that was the day they passed away. So we have that information here, whereas person number 4 had 3,747 days of follow-up. And on that last time, maybe they went for a visit to their clinic, and that we would mark as still alive at that point. And so survival data, what usually you need is a day of follow-up or time of follow-up. You need an endpoint, like a outcome, which is usually, it's a binary outcome. It's your event of interest. In this case, let's say death or not. And then there's this idea of censoring, which means if we're looking at days till someone dies, so risk, basically true survival, and we saw that fourth person at day 3,747, and they're still alive, that means we haven't observed their event. They've been censored at that time. And that's really important for survival analysis. And what makes it different is that we are not able to follow that person any longer. We don't know what happened. They could have died the next day, or they could have lived another 20 years. You don't know. And so it's a very unique type of data. And it takes very unique types of analyses that takes into account that information. And in R, it's very unique coding. So I want to show it to you because if you do survival data, it's odd the way that it's put into R, and I just want to show you the code. And if you haven't seen this data and it's very boring, just to zone out for a little bit. But I just want to show you the code and then a useful function that I use to visualize this data. So let's pretend that what I was saying about this data is true, where we have time to event data in this data set. The outcome is vital status after a certain number of days, and that column days to last follow-up is specifying how long we've followed that person. And so we need to create our data in a certain way to use the survival modeling techniques. And what we need are two things: event status, which is 0 versus 1, which means 1 if we observe the event, in this case, whether we observed that they died, 0 if we did not observe that event. And that could be that we followed them up and we didn't observe their death by that certain time. So that's the first column I created. So I called that event status. I used my trick of creating a 0-1 variable where I said 1 if vital status equals dead, double equals. It's going to be 0 otherwise, because I know it's a 2-category variable. The second type of column that we need is a days to last follow-up that is telling me the days to the event or the days till the censoring time. And this data, what I assumed about this data, if you're actually doing an analysis, you should know these things, but for this educational purposes, I assumed that if we have no days to death column, so that was the other column that actually I didn't talk about. Here, we have a days to death column and we have a days to last follow-up column. And so what I'm assuming is for person 1, because they had vital status dead, that their follow-up time is 371. And so we followed them 371 days, and that was the date of their death. Same with the second person, and followed them 136 days, and that was the date of their death. But the fourth person was alive. And so that means I want to, when it's NA, when this value is NA, I want to then look in this column, days to last follow-up, and look for that person's number. So 4, again, that was that fourth person that we followed for 3,747 days. We did not observe a death in that time, and they were still alive at that point, and we don't know what happened after. So that's what's going on here. I'm saying if days to death is missing, then I will take the value from days to last follow-up column. However, if days to death is not missing, then I'm just going to use that. I'm going to stick in that value that I have. And so that's what I'm calling event time. So I have my two new columns, event status, event time. Let's look at those. So you can see, oh, yeah, you have a comment that you in your MPH class, you saw survival data. That's good. So I won't be totally talking about crazy things. Event status here, you can see is 0 and 1. And it's 1s when we have deaths, and alive, those next 2 people who are still alive, 0. And we can see the first 3 people, I took their day of death, and then those next 2 people, I took their days of last follow-up. So when you're doing survival analysis, it does often take a lot of creating data. And oftentimes it's like dealing with dates. So you might have date of study start, you might have date of study end, and then you might have date of event or date of censoring, like maybe they dropped out of the study. So if we get to part 10, which I think we will get to some of it, I'll just briefly talk about dates in R, but there are tools to work with dates in an easier way. In this case, we actually have days of follow-up, which is nice. It's not always true to have that column. So we don't actually have to calculate number of days, but we have it, and still need to create that event time column. Okay, so keep those in mind. Those are going to be our important columns. And then the survival package in R is what is kind of the basic way of dealing with survival. So you do have to load that in. And it has a very particular way of specifying survival information. So like I said, we need an outcome variable. And inside that outcome variable, we need to hold both the event time and the event status. So it's like a composite outcome in a sense. So instead of having a formula like y tilde x plus z, we're going to have survival outcome tilde x plus z. And so we create that special outcome using this capital S serve function. And so let's just maybe just look at the documentation. The survival package has been around forever. So I will say it's one of those packages it's not that easy to find good documentation for. You really have to find examples of people using it, I think, to get good sense of how to use it, because it's very powerful and does a lot of different things. What I'm talking about right now is called right censored data. But if you have learned anything about survival, you may have heard that there's also left censoring, interval censoring, and a bunch of other stuff. Right censoring is the most common, where you like lose people to follow up, they drop out of the study, or your study ends. And so you're right censored. But there's this function can take all kinds of different survival data. So that's why it's so complicated. And so what we have here is we have our time and we have our event. And so that's what I'm specifying here somewhere. Here we have our time and we have our event. So I've said I want it to be the event time to be my time, and I want my event to be event status. So like I said, this is a bit of a mess to look at, but we don't usually write it exactly like this, as you'll see. But this is the way we use the serve function. I'll just run this. This is the output. And again, like I was saying, this, we don't really, actually, I don't know why that's there. That's weird. To check that out. Should be, I don't know, we'll see what happens. But this is what this really is showing, is all of your event times. And then there's a plus, I believe, if there's an event, or no, I think it's a plus if it's censored. Yeah, probably. So this was a censored person. So what I don't ever print this out, so I don't actually look at it, but this is all of your data. And so you'll see this is the way that we usually use it, inside of another function as our outcome in the formula. So you'll recognize this idea of having, like, this is our Y tilde, our predictors, our outcome, and then our predictors on the right side are independent variables. And in that, this kind of pattern will show up in the survival functions that we talk about. So like I said, survival functions within survival models take this special kind of formula argument, where the left-hand side is the survival object created with serve, and the right-hand side are your independent variables. So if we want to do the most simple survival test, is a log rank test comparing survival times between two groups. And so to do a log rank test, we use the function survdiff, like survival difference. And we use that formula, serve stuff on the left, disease is our predictor, our two categorical predictor on the right. And then I have to specify my data. If I specify my data, I don't need that $ business that I have up here. So if you look here, because I didn't have a place to specify data, I had to use the vector smoke complete serve $ event time. But when you use it inside survdiff here, after I specify my formula, I can specify my data that all of these columns are coming from. And so I don't need to use that $. So it's a little bit cleaner, a little bit easier to see, similar to when we did linear regression or GLM. If you specify your data, you can just use the column names here. So let's just run this. So this is a log rank test. You get your observed and your expected, and your observed minus expected, and all the stats stuff that you calculate. You get the N, you get chi-squared test from that, 2 degrees of freedom, and a very small p-value. And this was the 3 categories of disease. If you remember, we had like breast cancer, lung cancer, cervical cancer, I think. Which means that these 3 categories are significantly associated with survival time, which in this case is time to death, true survival time. And again, Broom gives us the nice way to pull out information. Though in this case, tidy doesn't give us what we want. We actually want glance, because this is really just a test. It's not like a model. We don't need estimates or anything. We just want the test statistics. Glance gives us the p-value. So that's a little bit unusual, but we do end up with our chi-squared test statistic, our degree of freedom, our p-value. So that's a log rank test. This is like the basic group comparison of survival time. And this goes hand in hand with Kaplan-Meier plots. So if you've done survival analysis at all, you've seen Kaplan-Meier plots. And usually a p-value with a log rank test is shown with the Kaplan-Meier plot. So I'll show you that here. And the way you build a Kaplan-Meier plot, which is a visualization of survival time, is with the survfit function. And so this is a function that is almost exactly like survdiff. So if you can look at the comparison up here and down here, it's like the same thing, except instead of survdiff, you use survfit. And I'm going to save this output, though I'll show it to you. Let's actually print it. And it gives you essentially a similar output, though here it's actually showing me the number in each group, events, and median survival time, as well as the lower and upper limits of the confidence interval around median survival time in each group. So that's nice, but what you really want out of a Kaplan-Meier plot is the plot. And actually, haven't done this in so long. I think plot works. Yeah. So this is the default plot you get from that model fit. It's fine. looks okay. We don't really know which group is what, so that's not useful. So what I use is SurvMiner is a package, and ggsurvplot is the function. So this is what I use to make survival plots. There's a many customizations you can do, but this is really tiny. But you can make tables, risk tables, and no. I wish I hadn't started doing this where it cuts off the bottom of my plot. Oh. Well, down here, there's a risk table, but you can't see it. But the idea is that you have your 3 groups. It actually tells you, it's probably really tiny, but the green is CESC, so I think that's cervical cancer or cervical cancer. BLCA, oh, actually BLCA is bladder cancer. So bladder cancer is the red line. LUSC, I think is lung cancer. I should have looked this up. I've forgotten. It's been a while since I looked at that data information. But we have the 3 different types of cancers. Bladder cancer, I believe, has the worst survival. Here you can see it has the lowest drop, the fastest drop, which means at day like 1200 or so, about 50% of people who have that specific disease type have had an event, so they've died. And so Kaplan-Meier curves are generally plotted against some sort of categorical variable. In this case, I plotted against disease. Sometimes you might have a binary or some like quintiles or something of some numerical predictor, but that's the basic idea, is that it calculates survival within those groups, and it gives you a confidence interval around that survival time. And so on the y-axis, you have survival probability. It starts at 1 because everyone is still alive at that time 0. And then as time goes on, it tells you an estimate of how many people are alive after that certain amount of time. And you can see the censoring on this plot in a very tiny little cross on the lines, which means that people have dropped out of the study or our follow-up time has ended and without observing an event by that time. So you can kind of see, I don't know why I can't get it to be bigger, but our, oh, no, come back. There it is. Okay, really tiny, but what this is showing is bladder cancer, skin cancer. Thank you. Okay, so thanks. BLCA is bladder cancer, LUSC is lung cancer, and CESC is skin cancer. I did not expect that. So skin cancer is the green. That makes sense. Skin cancer has the highest survival probability. And that's very tiny, so I don't know why it's so small. I think I have my figure size set as really big or something. But this is telling you the number of people at risk at each time point. So you have time 0, 2000, most people have either had an event or dropped out by that point. And then 4,000 days, 6,000 days, there's basically 1 person left. Not that many. All right, so definitely take a survival class to learn more all about this. So it's not a good explanation, but you can make nice plots with that package. It's the main point I wanted to make. And if you want to show overall survival, not separated by a category or anything, oh, this is probably why it's so small, so tiny, so this smaller. I've made my figure size kind of big. So what you do is put a 1 instead of a categorical variable. So let's look at that. That's just basically just saying we only want an intercept in that model, which doesn't have any grouping. So you can see overall survival across everybody here. Number at risk here. And the nice thing about ggsurvplot is there are many things you can change about it. Of course, the colors and the whether you want a confidence interval or not, and all kinds of things. So this, I just gave you an example of setting a bunch of customizations. This will only be useful to you if you're making a survival plot. So I don't want to go through everything, but I commented them to show you what they each do. And I'll run that just so you can see it looks slightly different. I actually don't think I changed much except the palette, the colors, and added some labels. And I changed one nice handy thing that I like in this function is that you can convert from days to years on the x-axis without actually changing your data. So now the bottom follow-up is in years, 0, 2, 4, 6, which makes a bit more sense than like 2000 days for example. You can add cumulative number of events and so on. So a lot of things you can add to these tables and figures. So I think that's probably the most common package these days to make nice survival plots, but there are a lot of other ones. So if you come across them, there are more like ggplot focused ones. This one is actually made in ggplot, so a lot of it is based off of that, but it's just very handy. And then the last thing in survival that I want to cover just how to do is a Cox proportional hazards model. So now going back more into the regression world again. So this is actually a semi-parametric regression model, which you will learn about if you take survival class. But it's a similar idea. It looks similar to the code we just saw above, though instead of servdiff or serve, whatever the other, serve fit, now we're using Cox PH. So Cox PH is the method or the function that will fit a Cox proportional hazards model. Again, you have your serve object as your outcome. I'm just going to use disease again, just so you can see what it looks like in comparison to what we've done. And then I'm going to use broom tidy on my output so you can see it as a table. So we end up with, in this case, we have a predictor that is a 3 categorical predictor. Similarly to how we saw the categorical data in, I think we had one in logistic regression maybe. You have a reference group. In this case, it was, look at my cheat sheet that Joseph sent, bladder cancer. And so we're comparing skin cancer to bladder cancer, lung cancer to bladder cancer. And we have an estimate, which is the log hazard ratio, comparing CESC to bladder cancer. So this is negative, which means it has a log hazard ratio of negative 0.9. And then LUSC is negative 0.27 hazard ratio. And so it's hard, I mean, log hazard ratio, it's hard to think in terms of log hazard ratio. So what I usually look at is the actual hazard ratio. And so you can exponentiate it, true. I also wanted a confidence interval because I like to see that. So this we can see that the hazard rate is about 40% in people with skin cancer compared to people with bladder cancer. So again, even just looking at that plot, bladder cancer did have the lowest survival. So that's saying that people who are diagnosed with skin cancer have a pretty much lower risk of death than people who have been diagnosed with bladder cancer, which is what this plot is telling us and what that estimate is telling us. And then lung cancer people are somewhere in the middle. Their hazard ratio was 0.7. So it's about 76% of the risk of people who have bladder cancer. And so yeah, so your hazard ratio is less than 1, which means you have decreased risk of the event, which in this case is death. And that's kind of nice, but again, I really much prefer to see the GT summary version of this output because you get a little bit more information. You see the reference group for one, which is really nice, especially if you're showing this to someone else, and you get the confidence interval. I think I can exponentiate in here. You could also get hazard ratios by setting that setting here. Hazard ratio and confidence interval, both significant. Okay, so this is just your turn. If you want to think about it, let's take a break maybe and come back in, let's do like 5 to 6 minutes, like 4:21 or something. Come back and you can look at this if you want, or we'll talk about it when we get back. All right, so back to last bit of survival. There's a comment that basically, my comment really is that survival is very hard. When I did my dissertation in biostatistics, it was sort of like a kind of a joke that only the really smartest people did their dissertations in survival data, because the theory behind it is very difficult. So don't be sad if survival analysis is hard, because it is. And I think you really need to spend like a full quarter or semester on it to really get all the nuances of how all the estimates are created and what even is hazard rate, that I'm still sometimes struggle with. But it takes time. So for serve diff, which is our log rank test, again, it's the same outcome as before. So we had our event time, event status, I guess. But in this case, we want to test for association of survival time with gender, which I think was just called gender, remember, right? And then that's true. So this gives us another significant, very significant p-value. We can see there were more male versus female patients. 3 were deleted to missingness, that's fine. If we look at the, let's just look at the Kaplan-Meier plot of that here. Serve minor, GG serve, oops, not minder, serve minor, GG serve plot, and data. Look at it, and we can see, you can see by default, it doesn't give me the confidence intervals, so I can't totally assess whether they're statistically different, but our log rank test told us that they were, that male patients had lower survival than female. And then we can do the same thing. I'm just going to copy this, so I don't have to type it. For Cox proportional hazards regression, I also want to add in disease. Oops, disease. I forgot what. So I think cigarettes per day is, yeah, cigarettes underscore per day plus cigarettes per day. Oh, and age. So if we look at that, oh, I can't spell. If we look at age at diagnosis, isn't it? Look at that. This is going to give me the GT summary output. And we can see that once we put all of those in the model, that disease becomes less significant, and actually the comparisons between skin cancer and bladder cancer is no longer significant, but gender still remains as a significant association, and age as well. The cigarettes per day is not at all. So that tells us there's more to the story than just what diagnosis they have. And that there might be other confounding factors that are affecting survival. And obviously, age will affect survival no matter what your event is. Well, especially if it's related to mortality. So that's just something to think about, be aware of. Okay, so that's all I have to say about survival. Like I said, it's a difficult topic. You should take a full class on it if you can, if you want to learn more about it. And I don't know when Jody Lapidus, I think, teaches that class in the spring or winter. I don't remember, but I think it happens every year in the biostat world. Winter. Okay, so right now. Oh yeah, I think that affected this timing of this class, actually. I remember that now. All right, so how is it? We have a little bit more time to talk about this. I wanted to, this is something that isn't talked about much in regular biostat classes, but it is something that I do in R a lot, which is power and sample size calculations. There are many packages that will help with this. I'm showing one called PWR, but there are a lot, and it really depends on what your model is and what kind of what your data looks like. And so this is very quick, just example, just so you know that these methods exist. So power and sample size is something that you do when you're designing a study. You think about how many subjects or how many mice or how many whatever you're studying samples you need to be able to detect a certain effect or association. And so, like, for example, if you're just doing a simple two group comparison of a continuous number across your two groups. You would use a t-test, and then you would use that idea, that fit and statistic to calculate the sample size you need, depending on some factors. So let's look at our data again. So we have let's use the PIMA diabetes data, looking at glucose as our outcome, or our group, our continuous value, our diabetes as our two groups. And if we run that t-test and look at the tidied output, we can see the p-value is extremely significant, as we've seen before. And so that makes sense. Glucose and insulin are highly related to diabetes status. But so when we're designing a study and we're trying to figure out what tests we're going to run, if we were designing a study to say, what sample size do we need to determine a difference in glucose between diabetics and non-diabetics, we need to know what that effect size is. For a t-test, it's pretty common to use something called Cohen's d, which is actually the ratio of the difference of means to the standard deviation, usually the pooled standard deviation across groups. So there are variations on the theme. And so that gives you a sense of like, how big of a difference do you see compared to the variability? So that's why it's a ratio. It's telling you, let's say the difference in means is 0.5 times the standard deviation, which tells you that compared to the variability in the data, you can see a decent difference in means. And so there's actually rules of thumb about what a small effect size is, and a medium effect size, and a large effect size. And you can take all that into account when you're designing your study. And then there's also the factor of how much funding do you have? Can you afford to recruit 5,000 patients or whatever you need? So there's a lot of factors that go into planning a study, but actually calculating an effect size is one of them. So if we're trying to figure out an effect size from a data set, what I usually do is, first of all, thinking of this as like a pilot data to design another study. If I look at my outcome, which is glucose, and I want to know the mean and the standard deviation within my two groups, diabetes and yes, no, I can use summarize and look at that. And so here I've just calculated mean glucose, standard deviation. I can see that in positive patients, it's on average 142, and in negative patients, it's lower, 110. And the standard deviation is about 25, 30, not too different between the two groups. And so if we calculate Cohen's d, what we would do is subtract 142 minus 110. So we'd get about 32, and then divide by the pooled standard deviation. I would guess the pooled standard deviation is in between this, let's just say 26 or something. And so you can see that the effect size is going to be bigger than 1, because that difference, 32, is bigger than our pooled standard deviation. And we can calculate that. So to calculate it, I first calculated, I took from that summary output, I filtered diabetes equals negative. So I took that row, and then I pull mean glucose, which means I pulled this value. So if I run this one line of code, I'm going to print it for you, show you that is what it is. It's this 110.6. And then I do the same for the positive. And then I calculate the standard deviation. So I need, because I had my standard deviation separated out, I need to recreate a summarized table across the whole data set, not grouped by diabetes. So I summarized SD, and I did the same thing. I pulled out that standard deviation. And so the standard deviation pooled was actually 30. So it's about the same as the positive people. And then Cohen's d is my effect size. So I subtracted the means and divided by the standard deviation. And like I said, it's about 1. It's a little bigger than 1. So that's a measure of effect size. That's actually a big effect size. That's why our p-value is so absurdly small. In general, can't spell, 0.2 is considered small, 0.5 medium, 0.8 is large. Those are like kind of the accepted rules of thumb. And so for power calculations, I mostly wanted to show you this because obviously we were very well powered to see that difference. It was a big effect size. Our p-value was very, very small. but we don't always get the luxury of having such a big association. And we have to really think about how to maximize our funding and get the sample size that will give us the information we want, and not waste our money, basically. So for power calculations, we do need an effect size, but we also need to think about the other factors. So there's N, which is the sample size. That's like our question, how many subjects do we need? The effect size, so in this case, for a t-test, it's either we're thinking about the difference in means or the effect size, Cohen's d. We need to specify the significance level, which is our type 1 error. So usually that's our p-value cutoff of 0.05. That means we're making our test pretty standard way of testing is using that threshold as a p-value less than 0.05. We consider it significant, which controls our type 1 error rate at 0.05. And then power is the probability of rejecting the null hypothesis when the true effect size is at least as large as the specified effect size. So that just means that if we have a observed effect size at least as big as the one we are hoping for, we will be able to reject that null hypothesis. We'll get a significant p-value with that amount of power. And so usually power is set to something like 90% or 80%. 90% is kind of the more acceptable level. Though I've seen many times having to drop it down below that just because of funding and whatnot. And so you're either specifying all of these things except one, which usually, depending on which way you're looking at it, is either sample size or power, but you do need to know all the other values if you're calculating this. So for example, if I'm trying to figure out what my sample size is, I would specify the effect size, the significance level, 0.05, and the power. And I'm going to say I have 90% power to detect this effect size, so I need N, and N is the question. And so like I said, we were very overpowered for that t-test. We had, what was that, 500 in the negative group, 268 in the positive group. If we calculate power, so the way to calculate power for a t-test is using the power.t-test function. And so I'm going to ask the power to detect that difference with that standard deviation and a significance level of 0.05 with N equals 20. So suppose we didn't have 568 and 200 in each group. Suppose we only had 20 in each group. We had much lower sample size. Power.t-test, you can either specify delta in SD, which is the difference in means, or you can specify delta as the Cohen's d and assume that the standard deviation is 1. So this is equivalent because it's all that really matters is that ratio. That's why we use that ratio as an effect size. That really drives the power. So let me just run it so you can see what happens. So I ran this first line and it told me this are the specifications I gave. N equals 20. The difference in means was about 32. The standard deviation was 30. Significance level was 0.05. I specified all this. I also asked for the last thing, which was power. So this is what it calculated for me. It told me I would have 90% power if I only had 20 in each group, which means that if that was purely the effect size I was trying to detect, I did not need that many people by a long shot. I only needed 20 in each group to have a good, decent amount of power. So this just shows you that the size of your effect really drives your sample size calculation, because this is such a big effect size. We don't need that many people to detect it. But in reality, we don't see that big of an effect size that often. And so like I said, I specified the difference in means and the standard deviation, but that's equivalent to saying delta, the difference in means, is that Cohen's d ratio, and the SD is 1 because it was 1.03 times the standard deviation. It's the exact same calculation, so either way. And the reason I talk about Cohen's d is because there are other, if you were to try there are many websites that will calculate power for a t-test for you, and they often ask for Cohen's d as opposed to the mean difference and the standard deviations separately. So I just wanted you to know that these two ways of specifying are the same. Once you calculate this, you're kind of good to go. This is the function inside the power package, power : power.t-test. And this does the same thing. So I'll just run that. You get the same power. It's just a different function. And it actually specifically wants D. It wants your Cohen's D. So this is the version of calculating power based on a sample size that I give it. But you could also flip that question upside down and say, what if I want 90% power? What sample size do I need? And so actually, let me just run it, because we know with that previous effect size, it's about 20. So my previous Cohen's D, if I run, then the way you ask that is that you leave n blank. You don't specify n, but you specify power instead. So up here, I specified n and then didn't specify power. That's telling R that I want to get the power out. Here, I'm specifying the power and not specifying n. And so it should give me n. And so yeah, it's telling me n is 20.5, which means if you have 21 in each group, you'll have more than 90% power. And so that's the effect size, 1.03. But what if we had a small effect size, 0.2, based on those rules of thumb? 0.2 is a small effect size. It's a very small difference compared to the standard deviation, only 20% of the standard deviation. So what is n there? Now we need 527 people in each group. So way bigger than 20 to get 90% power to detect a small effect size. And usually when you're doing a power analysis, you probably are trying a bunch of different numbers to get a sense of like how your sample size is affected by your effect size. And maybe you go, things that happen to me, I come back to my collaborator and say, well, you need 527 people in your group. And they say, there's no way, we can't even recruit that many people. There's no way we could get that. And so we have to come back and say, well, okay, you can lower your power. That's one option, 80%. Or you can say, I can only detect a medium effect size or a large effect size or a very large effect size. So I need to calculate power and sample size on a variety of parameters. And one way that you can do that is actually using the tools that we've learned so far, like MAP or versions of that, to first make a table of parameters and then map this power function onto those parameters. And so that's what I'm doing here. I'm first using this function called crossing, which is in, I don't know which package this is in, tidyeval. And so crossing, like expand, do the same kind of thing. Crossing takes two or more vectors of data or information and makes all the possible combinations. So what I'm saying here is I want to check sample size for all the combinations of these effect size I specified, small, medium, large, very large, and then two different power values. So this isn't a table yet because you can see they're different lengths. So I can't say like as Tibble or Tibble because it's not going to work because I only have 4 in the Cohen's D and 2 power values. But if I use crossing, what happens is it takes all the combinations. So you can see it said for Cohen's D 0.2, it gave me power 0.8 and 0.9. For Cohen's of 0.5, it gave me values power 0.8, 0.9. So I want to calculate what sample size do I need in this scenario? What sample size do I need in that scenario? And so on for each row. And so this will give me a sense of how these values affect my requirements for my study design. And so what I am thinking from here is I have a tibble, I have a data frame of all my parameters. I want to add a column that's basically like n, or n per group, and it's telling me the number of samples for each setting. So the way I did that here, first I want to create one setting. So just to kind of come up with the code that I need for that first row, and then I'm going to apply that to every row. So this is the way I usually build up to like an iteration or an automation step. I first try it out on one data set or one piece of data set, and then figure out how I'm going to get the information I want. And then I use MAP or whatever I'm using to pull out that data and run it over a bunch of different values. So let's just pick one power, one D value. So I'm taking the first parameter for the power value, the first Cohen's D value. So just saving those as two things. And then I'm going to use power t-test on that. So let's just look at what that output looks like. So this is saying power t-test says 393. So my D was 0.2 and my power was 0.8. So that's comparing, if we think about what it was, like 568 or whatever for 90% power with D equals 0.2. If I only have 80% power, then I only need 394. So I've already lowered my sample size. And again, this is like the printed output from that test. What I want to get is N. So how do I pull out that N from this output? Because that's what I want to fill up my column with. So I use tidy, which gives me a tibble. I can see it. There it is. I want that. So I use pull N to get that out. So if I run that whole thing, now I have a number, 393. So I want to do this for every row. I want to iterate over this index, pull out the power, pull out the Cohen's D, then run this code and get the N. And so the problem is that I can't just put in a whole vector here. I can only put in one value here. I can't put in the whole vector of power values, or I can't put in the whole vector of Cohen's D. And so I need to do this in an iterative fashion. And this is what I mean by like putting in a whole vector. This isn't going to work. If I try to run this, error, you need exactly one ND power and significance level must be null. And it didn't know what to do with this thing, which is a vector. I didn't like that. So I can't do that. That also means I can't use mutate just on this code. Like it's not going to give me, where's M? It's not going to give me like the right thing. It doesn't know how to take a vector and give you back a vector. And so we have to use map. And I haven't shown this function yet, but I think it's useful to know. I didn't want to confuse you when you were talking about map, but there's another function that's called rowwise, which is basically telling R, I want to use map on every single row of my function. So this is like a wrapper, kind of like a shortcut to using map on every row of a tibble. So what I do then is say the name of the data, pipe rowwise, and then use mutate. So this is a shortcut way of taking a function that is not vectorized, that you can't input a vector. It's going to break. Actually, I didn't run this. I don't remember what error, just a bunch of errors. Yeah, even like what even is that? It's the errors are terrible. But what this is really saying is it can't take a vector. It doesn't know how to deal with it. So instead of doing that, I stick in that rowwise. And now if I run this, it's taken that function and applied it rowwise to every row and pulled out that N. Now I have a nice tibble of every N value that I need for every setting. And I did show you the way to do that with map. You can use map in the same way, but it's a little more complicated because you have to use map 2 because we have 2 inputs. And so I like rowwise because it really simplifies it. I didn't even use map in here. I just used mutate like I was always using mutate. And this is the function that I used with my data. So it's just a lot more simple. Map 2, similar to how we've used it before, where you specify your column names and then your function with your .x and .y. A little bit messier. Does the exact same thing though. So this is just what I just had. So I'm saving it as that tibble. It's the code I just ran. And just to show you what I would usually do is make a plot of this. So this is the sample size data with the N. On the x-axis, I have my Cohen's D, my effect size. On the y-axis, I have the N that I need. And then I've colored it by power value. And so you can see when I have a very small effect size, I need very large sample sizes. But as soon as I start to make my effect size more reasonable size, that N per group drops a lot. And so I've actually zoomed in this plot because it's really hard to see what's going on down here. So to just show you between like 0.5 and 1.2. So this is a medium effect size, kind of more reasonable. This is where we were with our glucose and diabetes data, about here. Like we calculated, we only needed about 20 sample size in each group to detect that effect size. And then when you're back down to like 0.5, it's more in the range of 60 to 80. And so the way I zoomed in is I reset my X and Y limits. There are actually two ways to do this, to zoom in on a plot, using XLim and YLim, or this function called chord Cartesian. The difference is that this actually removes all of your data outside those numbers. So you have to be careful if you're doing this like with a box plot or histogram, not a histogram, density plot maybe, things that depend on all the data to make the plot. It's not truly zooming in, it's like removing everything out of that window and showing that data in that plot. So to be safe, sometimes it's probably better to use chord Cartesian because that really just zooms in. Like you can even see it sliced my line. It's compared to, let me run both of these. You can kind of see the ends here. It's put the dot here because it removed everything over here to the left of that line. But here I just zoomed in literally on that space. So you can specify XLim and YLim and zoom to see it a little bit better, because up here you couldn't really, this is what I'm zooming in on. It looks very flat and hard to see. So that was a very simple power and sample size calculation summary, I guess. But look at the package power has a lot of other like power. What else is there? There's the ways to calculate effect sizes in there, and chi-squared test and ANOVA, proportion tests and everything. So if you're ever designing a study and you need a power function, there's some good simple ones in there. But if you need a more complex power calculation, there might be an R package for it, or you just might have to use a different software. It depends. All right, so that is part 9. Are there any questions before we move on to part 10? Here I had a kind of wish list of topics. I have a few of these in part 10, just briefly. There are a lot of things to learn, but I have a link here. There's some good kind of just like a collection of learning materials, what they call intermediate topics that you might want to look at if you're interested in learning more. Okay, so where's part 10? Oh, I guess I did forget to say, the other thing I wanted to mention is that in the readings, this is the class, this was the readings for part 9. I actually updated some of these today, I think, which has like a lot of links about more learning in terms of machine learning and modeling, and more, this is more about functional programming, functions and nesting and mapping and all that stuff. And this is a good way to learn row-wise, which I think is really handy. So if you're interested in more, there's some links here as well. All right, so chapter 10 is somewhere. Okay, so part 10 is kind of like a loose ends situation. I just put in some random stuff that I wanted to talk about briefly with you, just so you're exposed to it. The first thing is this idea about what your markdown looks like compared to what your HTML looks like. And I will say that I have some certain things that I like to put in my markdown to make it look a little bit different than what I've been showing you in class. So I put that in this one. So this is part 10. It should be up on Dropbox. There should really just be a couple. You just need this one, this R markdown. Actually, let me save this before I forget as my own thing. part 10. So in this markdown, you'll notice a couple different things if you've been looking at the YAML and the setup chunk. The first one is I added this code folding hide, which I'll show you what that means. I also added numbered sections. I like to number my sections, personal preference, as you'll see what that HTML looks like. And I also really expanded my knitter options. So usually I just say something like eval equals true and echo equals true or something, I don't even remember. But here I've added a lot of options. And what this does is it sets default code chunk options in your markdown. A lot of these are the regular defaults, but I put them in here just so you know that you can change them. And then if you don't like this for a certain code chunk, you can override it in the like example here. I've set the code option to include equals false, which means in my knitted document, this code will run, but it will not be shown. It won't show up as in the HTML file. And the one that I use a lot is fig.path. What this does is it saves every single figure created by the output in this figure folder over here. So if you look, it automatically creates that folder. If I knit it, it puts every figure as a file. If I don't name the chunk, so this is like the chunk name here is set up, it saves it as unnamed chunk 26, whatever. It saves it as like a automated name. If I do name my code chunk here, I've named it scatter all pairs core. So as kind of a spoiler, here's one file that we will make. And it saves it as whatever file path is you've specified or like as the default. So this is a PNG file. So that's a nice way to just automatically save every figure you create in one folder. I do that for most of my reports. And I also specify figure height and width and some other things like the DPI. You can make this like 300 or something if you want high resolution figures. And those are the most important things, I think. So I will talk about the difference between like my teaching markdown and my sharing with collaborators markdown. The main difference is sometimes I don't show the code at all, in which case I will say echo equals false. But it is, in terms of like a reproducibility standpoint, good to include your code. So one way to round this situation where you have a clinician collaborator who does not care about your code at all, you would say echo equals true, and then you would say code folding equals hide up here in the YAML. And so if I knit this, to the minute, what that does is it creates a little drop down button that will show or hide your code. It's not beautiful, it's a little clunky, but it works, I think, for kind of an easy way to just hide all your code from the output. But the clean option, if you really just want a full HTML document that only has output, is to say echo equals false. And you can change that there. Actually, while I'm waiting for this, the other thing I often put in my first setup chunk is I set a default ggplot theme because I don't like the default one. So I put this here because I want all my ggplots to have theme black and white, or you can specify whatever theme you like. So I tend to do that just as a custom thing. Oh, where to go? Okay, so this is we had this. Oh, darn. I did the wrong thing. Hide. Okay. So this is my knitted output, and you can see up here there's a little button that says show all code, hide all code. So if I press show all code, you can see here the code has popped out. And if I scroll down, I can see code, but by default, it's all hidden. And so as I scroll down, I don't see any code, I just see output. But if I want to look at one of the code chunks, I click the code button. So it's a little bit annoying and it shows a bunch of code buttons, but it's still a nice way to just make it a little easier to deal with. And like I said, that setup chunk is not shown at all. I don't see any of that part about my options or my packages that I loaded or whatever. That all isn't shown, but the code after that is automatically shown. And then the other the other thing that I mentioned in the muddy points part was this DT package and the data table function, which is kind of like GT, which is a way to make HTML tables, right? Like make them look nicer, except you get a little bit more interactivity. So I can say, I want to show all of my data, which I changed to 50 because there's only 32 rows. I can go back to 10. I can search, I don't know, Valiant. I can search the data. So it's a lot more interactive, which works really well for big data sets. You can also sort, for instance, on MPG or whatever. So that's just kind of a little fancy HTML table if you like that. But my main tip is to not print regular output, because if you look at, for example, this result is not nice. I'm just printing some code output. I haven't cleaned it up at all. So you either need to just leave the code and hope that they understand what you're doing, or you really need to be careful about not commenting, but describing what you're doing in the text, or making it nicer by putting it in a table or a plot. I think those are the main ways to make things look a little bit cleaner. But you can see that this looks very different than my HTML or my RMD file. All the links are nice and linked, not looking, you don't see all that markup text. The bullet points are nice. Like I said, I like to number my sections. This table of contents is also one of the options in my YAML. Here, table of contents equals yes. I like it to float on the left side, and you can have it collapse if you want. So there's a lot of themes you can change. There's a lot of different customization there, but I really think it really depends on what kind of output you're trying to print and how you want it to look. But there's like a whole book on this one. There's a whole book on R Markdown if you want to learn about all the different options. And then there's a nice workshop working with Markdown and making different kinds of output, like slides and websites and all kinds of things.
Hey, Jessica?
Yeah.
Yeah, so I think as part of like my overall theme that I've asked you about with this. So for the problem that I've encountered is I'm the GRA for a large project, and my PI, I'm sharing this data with my PI. What I'm hesitant to do is to share my code with them so that then they can go and screw it all up, of all the work that I've done. But they also want to be able to like manipulate the data in the way that they see, so that they can get a sense of what's going on with the data and all that sort of stuff. So then they can tell me what they really want to do. And I'm wondering if this is sort of, I liked what I just saw earlier of like the sorting of kind of like all the data and all that sort of stuff. Is that sort of what you would kind of recommend? And is this, am I making sense as far as like what's going on?
It depends. Yeah. This is a common theme, especially when I worked with bigger data sets like omics data, where an Excel sheet is just not manageable for them to look at, and they really want a way to see their data. They feel very strong ownership over their data, and they want to be able to manipulate it and search it and like make some exploratory plots. So I think we have not really covered this idea of interactivity within R Markdown, but there are ways to build essentially mini Shiny apps, which is another thing I have not covered. So Shiny is a package in R to make web applications. And so what I've done with especially omics data, I developed a Shiny app that lets people upload their data and then search it and make some basic plots. So you could do something like that, where if you always have like a very specific type of data that they're working with, it makes sense to kind of generalize that problem. Maybe I'll just show you what I'm talking about. So you can do that in an R Markdown. You can make modules that visualize data or make it so you can search data, but you can also just build a standalone Shiny app or some kind of tool So for instance, this is with RNA-seq data, which is a type of gene expression data. So you're measuring expression of genes. It all looks it's like in the same kind of format usually. And so I created a tool where people can upload their data and then basically search and visualize it. And I knew exactly what kind of plots they wanted to see. So they wanted to see PCA plots. So I included that. I know they wanted to see, like if I pick a gene, box plots of the gene expression by a group. And so you can, if you really want to make this like easier for your collaborators to see the data, but they can't mess up the data, something like that is very useful, where you can give them this tool that lets them search and visualize the data, but not change the data, if that makes sense. Obviously, this is a lot of work and it's very time consuming and wouldn't be worth it for like one project. But if it's something that's happening again and again, and you can kind of generalize it, I think that would be a really useful way to work with people. And you can actually do that inside R Markdown. You can like merge Shiny apps with R Markdown in a way that you are able to search the data and visualize the data and so on. So yeah, there are a lot of ways to do it. We haven't really covered that many, haven't gotten to that point yet, but I think something like this also is just like a very simple way to let them search. It's a little harder to search here because we don't have that many character strings, but and you also can't filter. So you could build a tool where they could filter based on certain values, for instance, if that's what they were interested in. And Ted actually developed, I have to dig it up. I have a link. Ted Ladares, who taught this last year, developed an exploratory data analysis tool where you can upload your data and visualize it kind of in a similar fashion. So I'll see if I can dig that up. But I think things like that make it useful for just to see the data. It's a little easier than Excel.
Yeah, I appreciate that. It's been the biggest frustration for me. Like, I want to share this data with you. I'm sharing this data with you, and it comes back and you've changed my code, and now I don't know what's happened.
Yeah. Yes, I think I'm trying to think of like a way around that. I mean, yeah, you can give them your R Markdown and say, here, change things if you want, but then, yeah, you have to know what they've done. That actually is another kind of reason to use version control. So there's Git and GitHub, which are ways to track changes in your code, and you can like rewind, undo stuff that other people have messed up. But that is also another topic I didn't have time to talk about, but it is a very useful thing. It's another way to kind of just it's like Word track changes, but with all kinds of files. But yeah, I don't usually give that many people my code, so I haven't had to deal with that, luckily. Yeah, any other questions about that? I need to remind myself to find Ted's EDA link. Okay, so I have a few things in here. So I know there were some requests about machine learning. This is just the same, I think the same links I put on the website. So I put them here as well. Plug to watch last year's classes on tidy models. Very, very useful stuff. The third thing is dates. I wish I had spent more time on dates. I mainly put it off because they are tricky to work with. And LubaDate package is very useful. It's another tidyverse package that is used for dates and times. But if you think about dates and time, our calendar is not that useful or amenable to working with it as a data. If you think about what just happened with Spring Forward, that messes up time in terms of talking about difference in dates and like how many months are in between two dates or how many days are in between two dates. It all depends on leap years and spring forward and fall backward and all kinds of weird stuff that we do with our calendar. And so LubaDate actually is very powerful and deals with all of that stuff very nicely, but it is hard to talk about in less than an hour. So I just I'm showing you very brief introduction to LubraDate. Let me run my code actually. So LubraDate, I've loaded LubraDate. There's a cheat sheet that is useful to look at. All the RStudio cheat sheets are pretty useful. And so date is actually another object type in R. We talked about numeric and character, Boolean. Date is another one. So you can have a vector or a column in your data that's a date. And that has special properties. But for example, LubraDate, we could say today is a function that gives us today's date. You can save it. I'll save today as tday. We can look at the class. It's a date. So that, like I was saying, is an object type in R. Another function is now, which gives us the time as well as the date. And then there's all these different options, like you could set the time zone. So what time is it on the East Coast? It's 3 hours ahead. But the main way I use LubraDate is to convert data columns that are in date formats. And so those kind of dates can come in any different ways, as you've probably experienced. And so different functions will take different dates styles. So YMD is year, month, day. And it converts this character string, which is in the format year, month, day, to a date. And so I'll run that. And it looks the same, but what that really is that date. This is like the default way it prints a date. And so you can see that if I put slashes instead of hyphens and I don't use the full year, here I have month, day, year. Excuse me. So I use MDY, and that converted it to the standardized way it prints it out. And it is a date. If you try to give it something like, if you tell it that this is year, day, month, but obviously there's no month 19, it doesn't like that. And so it gives you NA. So you have to be careful that you are specifying your dates properly. But it also takes words and other kind of odd ways that we write dates. So that works, month, day, year. And you can also pull out information about specific dates or time points. So if I want the month or the week or the year or the day of that date, I can get all of that information, the 3rd month, the 12th week, the year is 2021, and the day is the 22nd. So this stuff is useful sometimes. This kind of conversion I use a lot if I have a lot of non-standard ways that people write in dates. And the other way that I use LubraDate is to essentially do math with dates. So take how many days from start to end, or how many days from study start to study end, or and so on. So for instance, if I save today's date and I subtract off year, month, day of January 1st, that will give me this output that says time difference of 74 days. Okay, so that's telling me there's 74, this is the 74th day of the year. But I might want that in terms of weeks, for instance. So there's a function in LubraDate called diffTime, which just means the difference in time. So you put your start date, your end date, and then you tell it exactly what units you want. So if I want to know number of weeks since the 1st of the year, that's 10.5 weeks. But you're probably noticing that this output is a little strange. It's not just a number, it's a sentence. And so looking at the class of that, it's actually diffTime, which is another object type that LubraDate has created. So if we wanted to if we're doing this inside a data frame, and we just want that number, we can actually use as numeric. And so that actually becomes handy with LubraDate, is if you want to really just like flatten it into a number, you can pipe as numeric on there. So there's a question, is there a way to change 21, 22 to 22, like flip the way that things are written? I think so. I think I'd have to look, I forgot how you do that. So what these functions are doing, so like this one here, It's what it's done is if I save that as my date or whatever, it saved it as a date object. So what this is really, without looking it up, the way I would do something like that is actually to pull out month, day, year, right? And I would probably use glue. So I would say, how do you want it? You want it year, and then month, because that's really, it's not the information anymore, it's a string. So it depends on what your purpose is. If I just want, no, I knew I'd forgotten one. If I just want a string that's in that format, like year, month, day, I would paste it together or glue it together as a string. But if I truly want the date information, I would use this function and then work with that date as a date. So there's like this idea of storing the information, and I would store it as a date, or printing the information as a character string. And at the printing part, I would use glue or some kind of like pasting together. But those two dates are equivalent, and they would be the same thing in LibreDate. And then you could fuss around with this to put a 0 in front if you wanted to do that. And so back to differences in time, that was a simple way to calculate the difference between today and the first of the year, 10 weeks, 10 and a half weeks. But if you're going anything more complicated, like a number of years or number of days between very long periods of time, what you really want to do is to use an interval. So within LibreDate, if you look at the cheat sheet or any documentation on LibreDate, you'll notice they talk about periods, durations, and intervals. And this all has to do with how we look at changes in time compared to the calendar, or clock time, as it's called. So periods track changes in clock times, ignoring timeline irregularities. Actually, I should just pull up the cheat sheet. Do I have the cheat sheet saved? Just so you can see the picture. Oh, where is it? Here it is. So periods track changes in clock time, which ignore timeline irregularities. They show you what happens when there's a leap year and how it calculates the interval between that. Durations track the passage of physical time, which ignores clock time, essentially. Intervals, which is what I want to talk about, represents specific intervals of the timeline bounded by start and end dates. So that's really in terms of like calendar time. So when there's a leap year, it counts a year from here to here. It skips the leap day, not skips the leap day, but like includes that leap day in the year definition. So like I said, LibreDate can get complicated when you start thinking about all these weird calendar issues that we have. But the way I use LibreDate is usually to calculate the time between study start and study end, or study start and follow-up date, or age often, and calculating someone's age based on their birth date and like the time of follow-up or date of follow-up or whatever. So let's say this person's date of birth is January 12, 2015. So I've saved that date of birth as a date. Diff time actually should work, but the maximum units are weeks, not years. So we can't calculate the number of years using diff time. We could like use this kind of hack to calculate the number of days and then divide by 365, or technically 365 and a quarter to count for leap years. But then it's like it gives us in terms of days. It's not good. So you can do that, but I wouldn't recommend it. What I would say is to use an interval. So interval is inside, is a function inside LibreDate. You tell it the start date, the end date, which I've set as today, and then you use this kind of odd operation, which is essentially dividing by the type of unit that you want. So this is actually a period. Years 1 is a period of 1 year. And I'll show you what the output looks like. So it's telling me it's 7.17 years. This is very, very close. So for all intents and purposes, same number of years. It's just kind of an odd way to do it. The official like lubridate way is to make an interval and then essentially modulate by the number of years that you want. And you get a nice numeric number out of it. So that's good. And so I'd say commonly I'm doing this to calculate years between two dates, which is someone's age, or calculating the days between study start date and the date of their last visit. So let's say they started the study in 2019 and ended in January 2020. I've written the date slightly differently, just that often happens, different date columns of different date formats. And then my interval is from study start date to date of last visit. And then I want it in terms of days. So if I run that, I'll see that there's 43 days since the study start. And you could do that with like more specific, sometimes you have date and time. You could do that with time as well and get number of seconds, number of minutes, all that. I don't do that very often, but it is something you could do. And the idea of an interval is also useful if you're interested in something like, say, you have two intervals and you want to check if they overlap or if they align in some way. So I created two different intervals, which based on all the values I saved, and then I used int overlaps to ask if those intervals overlapped, and it tells me true. It's a true false result. So I will say I've hardly ever done that, but it could be something that's useful in your work. But so that is a very, very brief lubridate introduction. If you really need to read one of these, I'd say either read the chapter in R for Data Science about it, or there's a vignette in lubridate. And then actually I found this book, which actually has good explanations of lubridate as well. So if you need to work with dates, sorry, it's not that fun, but it is possible and made a bit easier with lubridate. So yeah, let's talk about this and then have a break, and then we'll see how far we get in the rest of the stuff. So there was also a request, which I ran out of time to do, which is on how to read in survey data from kind of these publicly available survey websites. I guess I should make the caveat that if you're working with survey data, like true survey data, where you have a sampling scheme, you've like designed the survey data, you do need special methods for that, and you should take a survey class to learn all about that. But if you're just making like a silly survey like I did for the Google form for class, and you want to read in the data, there are methods for doing that. There's if you're working with Qualtrics data, there's a Qualtrics package. And if you're working with Google surveys, you have to use the 2 Google Sheets data. And when I thought I was going to talk about it, I made a couple fake surveys, and then I didn't have time to actually demonstrate it. But I did write the code, so you can see, like, if you do make a Google survey, it's very easy to make. If you go to Google Drive and say, I want to make a new survey, it's very easy to do. And then this code, if you read the comments, it talks about how you would read that into R. You first need to basically authorize R Studio to look at your Google stuff. So that's the first thing. The second thing is you need to find that sheet that has the results in it and get the ID out. And then you need to read it in. And so I did this already and I saved the results. And the survey I'm using is one that I made up that actually has, if I go to the link, I wanted at one point to talk about storing kind of complex demographic data, such as like race and ethnicity and sexuality and disability status and all those kind of very complex demographic values that are often not specified very well, especially in older data sets and older surveys. But there are actually a lot of people have done a lot of work in thinking about this problem and how do we collect this information and what are the best questions to ask. And so I've put a few links on here. Harvard's Office of Regulatory Affairs and Research Compliance created a nice kind of PDF, a tip sheet about how to collect this kind of data. And so I modeled the survey data after all of their tips. And so you can see when you're thinking about reading in this data, like these are checkboxes. So someone could specify both female and transgender, and that means your output is going to have those two values separated by a comma. So this can make very complex data that needs some complex data cleaning, especially with like the same with race. You could have multiple races and ethnicities and so on. And so I'll just show you, I just like clicked around and made a couple test values, and I loaded it in your part 10. And so when you read data in from a survey like this, it all depends on what you named all what your questions are. It's not very, you can imagine dealing with this data is not very fun because the column name is that full question. So it requires a lot of renaming all your columns, making sure you know what all your categories are. You might want to deal with the date and pull out the date of the time the person took the survey. And so it can get a little bit complicated pretty quickly. But this is what I used to read in your survey responses and make a summary sheet for myself. So I could pull out all your attendance and everything. But yeah, I don't really have time to go into all the details of all the data cleaning required for this, but I just wanted to show you that it is possible to make these surveys and pull them in if you want, and also to give a nod to the people who are working on this inclusive diversity demographic data. All right, so let's have another break, and then we'll talk a little bit about functions again. So I'll come back at like 5:28 and see you in a bit. I'm recording. So I put in the chat the link that I was thinking of. Ted Ladaris has created a nice little package called Burrow. I'll put it here for people recording. That basically, oh, not that one, the other one. That basically will create a Shiny app out of a data set of your choice, which is really nice. So that's something worth playing around with if you have this need to visualize your data. So the last section I called writing functions advanced topics, and there's no way we're going to get through all of this, but we'll see how far we get. I did just in this last half hour. I do want to at least mention and kind of briefly go over tidy evaluation, because I feel like I can't show you tidyverse functions and how to create your own functions and how to do them and just ignore the fact that putting them together is kind of hard. So I do want to just mention that if you do run across this issue where you can't make a function and it's not working, and it's probably because of tidy evaluation. So what does that mean? So we've seen a lot of examples of some functions, writing our own functions to do our own special tasks. But merging custom functions and tidyverse principles is not as straightforward as we might think. And that is because most tidyverse functions, or sometimes they're called verbs, use what's called tidy evaluation. So tidy evaluation is, in technical terms, is a special type of non-standard evaluation, which means the evaluation in terms of how your code is evaluated. And so there are two basic forms. If you think about how we use arrange or mutate or count, filter, group by, summarize, all of those use what we call data masking, so that you can use data variables as if they were variables in your environment. That is, you write the name of the column, like my variable, not df $ my variable. Because my variable, so we have like penguins is loaded in our environment right now, but species is not. If I try to say species, it's not going to find species. Penguins species does exist. That's available, but penguins is like your environment that you're looking for species. If you kind of old school, our coders will often attach a data set. I used to do this. I would highly not recommend doing that. Attach a data set basically means throw your whole data set in your environment. So now that species, island, bill length, all of that are in your environment, and I would be able to call species without doing penguins $ species, but that can create a mess somewhat quickly. If you try to if you edit the penguins data set, it's not going to edit your individual columns the way that you think it will. So it's it becomes complicated, and I just would not recommend doing it. It's better to keep your data sets contained. Don't scatter them to the wind by attaching them. Keep them as a data set and call those column names either with the $ or with your tidyverse data masking functions. And so this idea of writing the variable name and not the $ version is the main issue when writing functions with the tidyverse functions. The other type of tidy evaluation are verbs or functions that use tidy select, so tidy selection. So this is where we use things like starts with X or is.numeric or like how I use the colon, like age colon pregnant or whatever I said to pull out those column names. And so tidy select, we've seen different ways to deal with that, but this is the main issue. And so I'll show you an example. For example, this is simple tidyverse commands that we've done. Penguins, pipe, filter species equals gen2. That's filtering all the rows where species equals gen2. Select island species, count species. So here I've used what we think of as like unquoted column names. Those are the names of the columns in my data. I could run each piece of this and it would work. I could run it all and we end up with another tibble, but this doesn't work. Putting in quotes doesn't work. So if I try to run this, it doesn't know how to deal with these quoted column names. It doesn't know that's a column in your data. And so that is the disconnect between using a function with the tidyverse, because what's your input then? You can't input a column name as a character and expect it to work. You can't really input just a bare column name like species without the quotes. So looking at this function, let's say I created a function and my argument is the column name and I want to filter based on that column name equals gen2 and select that column name. So I would think I could try it and see if this works. I'm running that function on species without quotes. And I get an error, species not found. It doesn't know how to do this. We need something else. And so I would say, well, what if I put in quotes? That runs, but it gives me a tibble of 0. It's not actually doing what I want it to do. It does give us, though, this nice little warning, something about using an external vector in selections is ambiguous. You should use all of column name instead of column name. That's talking about this part, which select actually does work with a string. It's like it doesn't want to, but it does. But filter does not work with a string. That's the main error issue. So we have to fix this. And I will say that this is a complex topic. There's a lot more behind the scenes that I'm not talking about at all. There's a lot more different ways to do this, but I'm going to just show you the very simple workarounds. And then if you want to learn more, here's some background on that. Sorry, I'm losing my voice apparently. So the way that I would recommend to deal with tidy evaluation is to use the embrace operator. And it's a funny name and a funny situation or character. It's the double curly brackets. So that's the embrace operator. And so what we do is instead of just saying filter call name equals gen2, we say select call name equals island. Sorry, equals gen2. And then we select the call name in island. And so what that does is it tells it actually evaluate that as a column name. And so this does work. And then put the embrace around it. And my fun species actually works. It knows to look inside penguins for species and filter that. It knows to select species as a column name and also island, which I've left. So it's kind of a simple trick. It's simple to implement, and it looks kind of nice. What's going on behind the scenes is complicated to talk about, but it works. So that's my recommendation, is if you do need to make a function that works with column names, then just use the embrace symbol like that. And it works in a lot of different ways. Like you can use it in filter and select and summarize and all kinds of stuff. You can, if you format your function so that data is your first argument. So it's the same idea, the same function, but now instead of penguins always up here, always using penguins, I want to input data. I also added an argument called value, which I've put here. And so I can say, I'm going to run my fun on the penguin data again in species, and my value is Gen2. That should give me the same thing as above, which it does. But because data is my first argument, I can actually use it in a pipe. So whenever the data frame that you're kind of using in a tidyverse function is your first argument, you can pipe it. So that's what I've done here. This is the exact same thing. I've said penguins and then run my function. I've set column name equals species, and I've filtered species equals Gen2. So simple function, but it does work the way we hoped that it would work. You can get more complicated. You can use it with group by and summarize. Here I've taken a group argument, so group column name, put group inside the embrace. I want to take the minimum of some variable, some column name, and the maximum. So here penguins, I didn't do anything with NAs up here, so I just dropped all my NAs just to show you that it works. And then I run my function because data is the first argument. I can pipe it. I want to group by species, and I want to take the min and max of build depth. So that looks nice. Though this can be tricky because you can't pass characters. So if I tried to pass a character argument instead of a bare unquoted column name, it would do something, but not what we wanted it to do. Something very strange happened. And that all has to do with like environment and how it's interpreting those characters. It's trying to create new columns like that. And it's not doing good things. So you have to be aware that when you use the embrace, you're passing the bare column names in there, not the quoted column names. And you can also do tidy select, use tidy select type inputs. So here I've made an argument called summary variables. And that's going to be the names of the columns that I want to run my summaries. So if you have a specific, if you always like to show mean, min, max, standard deviation, you could create a function like this that always does the same thing over and over again. Here I'm just showing mean and SD. But I can put, because it's inside the embrace, I could use the tidy select type code. So here I've said, run my summarize function on every column that starts with B. So if we look at that, I've gotten the mean, standard deviation of all the B names, build up, body mass, etc. And I grouped by, I did that first, grouped by species. So you may not see why you would want to do this, but I mostly wanted to show you that it's a possibility and it's not actually that tricky. You just have to be careful with this embrace function or operator. And a slight aside also on that, if I wanted to use the embrace operator to, for instance, in mutate, and I wanted to mutate a column in place. So I want to create a function in this case that divides my column by some factor. Here, the default is 10. But I need to specify a name inside mutate. If I pass var without the embrace, it's not going to know, it just doesn't know what to do. But this will this kind of trick will make that name equal to the variable name you specify, but you have to use this another special operator. You have to use the colon equal sign for this to work. If you use regular equal, it doesn't know how to evaluate it. You'll get an error. So for instance, if I just rescale bill length by 10, it's actually, let me first look at penguins. So bill length, you can see is in millimeters, 39, 39, 40. If I run this, it's divided it by 10, 3.9, 3.95, 4.0. I can also divide by 0.1 to put it in centimeters. So now that's not true. This was centimeters. I don't know what this is. 391 somethings, and then 395, 403. So I multiplied by 10. So this can be handy if you want to use a function that is mutate. Basically, you need to use this little special equal sign. But I will say, I don't do this often, but I do often make functions that output plots. So I think this is the key usefulness, because often I have a certain type of data and a certain type of plot, and I want to make that plot many times. And then know how to get my column names into ggplot through a function. It is the same issue. So again, ggplot uses our unquoted column names, right? We put in body mass G, bill length MM. That's how it knows what columns to plot. So let's say I just want to make a scatter plot, simple color by species. Why that's taking forever. You can see, because I've set up high in my YAML, not my YAML, the knitter options, I've made my plots really big. All of my plots are scaled really tiny, which is not useful for teaching. Probably shouldn't have made it so big. But this is my scatter plot with 3 groups. You can see that it has nice correlation. But so if I want to run this scatter plot on different X and Y axes, and I wanted to create a function where I put X bar and Y bar, and I tell it which variables I want, this won't work again because of the tidy evaluation. So same issue. You can't just expect R to understand that. You have to use the embrace operator in the same way. So X equals X bar with the little curly brackets around it, Y bar with the curly brackets around it. This will work. So let me run that. So I run scatter fun. I've given it the bare column names, and it was able to make that same plot. And so I could change that up. I could put flipper length MM, I think is 1, and I get a different plot with the same different x-axes. But this, if I put in quotes, still does not work. It gave me a dot. So it has to, when you use the embrace operator, you need to give it the bare column names. But I will say that I actually don't do that very often. What I usually want is to give it character strings, because usually I'm like pulling out the column names and then feeding my function those character strings. I'd say that's 95% of the time the way I'm using functions with ggplot. And luckily, ggplot actually has a helper function that does this for us. So if I want to say if X bar and Y bar are character strings in this case, I would use, instead of AES, I would use AES _ string. And then X bar and Y bar can just be how they are. You don't need the little embrace symbol. And so that means that this implementation works. If I put quotes around the column names and use this scatter fun string that I've defined here, now, because of this AES string, instead of AES, it gives me the plot. And the reason, I'll show you in a bit the reason why this is useful, but first, just as a side note, because the output is a scatter plot, like a ggplot plot, it's a ggplot plot, it's a ggplot object, I can layer on top of that as well. I could add a title, any kind of things that you would add on top of a ggplot you could do. So just as an aside. So because I want to pass a lot of different values, I want to make a lot of plots kind of automatically. The way I would do that is probably to use map. I would create a list or a vector of the column names that I want. So here I want bill length, bill depth, flipper length, and I want to plot all of those against body mass. So if you look at my function, the first argument is xvar. So that's the x-axis. The second argument is the y-axis. So when you use map, this part here, this part that's specifying the list or the vector is going to go in the first argument of your function. So if you've done the final, that's a key thing you need to realize for the first question is that that mapping, if you have a function that has multiple arguments, it's putting that data into the first argument. So these are all my x variables. This is my function. And this, I'm saying I want y var to be always body mass G. Make this smaller. It's bothering me. There we go. So if I run this, I've applied map. I've created 3 different plots. And then I used ggpubr, ggarrange to plot all of those plots. One thing though is they all have the exact same legend and gets all smushed. And so there's an argument in ggarrange that says common legend equals true and puts the legend up here. So that is a very nice thing. Still cutting it off though. Well, this happens every time. But down here is the other one. So there's 3 plots. They all have the same y-axis. That's what I specified, body mass G, and then you have all your x's. And so this can be handy. Here I have an example. I don't really want to go through this because it's complicated and I kind of want to skim the other stuff, but there is a way if I wanted to do all the combination pairs of my column names. And so if you're interested in that, I'll just run the end of it. But if this is code to make all possible pairs of column names. So I've created using the comb n function, which you can read about, all possible pair combinations of the column names I want to plot. So this, I want to make a scatter plot of this, and of this. Oh. So where this is my x-axis and this is my y-axis. And so again, I use map, but I need to use map 2 now because I have 2 lists. And I run that and I can get, again, the list of all those plots and then plot them in ggarrange. And so you end up with all the possible combinations. So that can be a useful thing if you have a lot of data and you want to look at a lot of different scatter plots. Just make a kind of an automated way of making the plot that you want. I wish this would show all of them. But you have to imagine what it looks like, I guess. So this, I'll just say, because we only have like 10 minutes left and I don't want to go through too much in detail. This is a way to pull out all of the correlations. So here I'm writing a function that makes that same plot, but then also pulls out the correlation test, correlation and p-value. So we looked at correlation plots like core test and, not core test, what's it called? Core plot, GG pairs. Those functions will create correlation matrices and plot them for you. But there's also ways to actually test correlation. So you would calculate correlation and then calculate a p-value that's the test of whether that correlation is significantly different from 0.5, it's a 0.0, I think. So core test is the test that you want. So core dot test, sorry. So that's just a function in stats that you can run and get the p-value out. And yeah, so it's different from 0. It's testing whether the correlation is different from 0. So I'll just run this. It pulled out the p-value. And no, I didn't run this. I created my own function. What's happening here? Here. And this is what it does. I'll show you how it runs on 1. And it makes the same plot, but it puts, it's so comically small. Get bigger so you can see it. It puts it on, a little better, on the subtitle. So I've pulled out the information using tidy and pull, and I used glue to make a nice kind of summarization. I put the correlation and then the p-value. And so this is just an example. I just wanted to have an example here for you to see that that's kind of what I usually do. I pull out some summary information such as correlation and the p-value, say, and then I plot that visualization of that statistic. So in this case, correlation is 0.6, and this is overall correlation. I didn't separate it in groups. And then you can see the group-wise associations in the scatter plot. And by group, I mean species. And so we can map that and do that for all possible pairwise combinations. And you can see, sort of, partially, you can see some of them. Up here, correlation, p-value. And so I had a question in the text, what's going on with these negative correlations? It looks like everything's positively correlated. So for example, this one, correlation is -0.2, p-value is very significant. And that's because if I didn't have those groupings here, the correlation would look like the opposite direction. If you imagine that there were no colors, you would see a negative correlation. So that's called Simpson's paradox, which you probably learn about in SAT 101. That's a good example of what happens if there's some kind of grouping confounder that's changing your associations between two variables. So overall correlation is negative, but once we look inside species, the correlation is positive, very positive, and significantly so. So it's always a common stats lesson. Okay, so 5 minutes left. In here, there's some tips about debugging, which if you are working with your functions, you should at least look at some debugging methods, because otherwise you'll be very frustrated. And then an aside that functions can take function names as well. So I'll just show this very simple example. Here, I'm inputting the name of a function and a vector. I'm converting the vector to be numeric, and then I'm running that function. So I could say my fun, which is the name of the function, and then mean, and then a vector. So just to show you that you can not only pass vectors in data frames, you can pass different kinds of objects like function names, ggplots, whatever. Very, very flexible. So this is about taking functions as arguments. I knew we wouldn't get to all this, but I wanted at least to have it as an example just in case. And this is all about debugging. But debugging, there's a lot. You can read a chapter about it in Advanced R. There's a lot to think about when you're thinking about debugging, which just means figuring out where your error is coming from. But I tried to share some tips if you want to read that. And then the last couple things down here, I gave a link to the tidyverse style guide, which is kind of nice to know, just like how to make your code and markdown code more readable and tidy and kind of standardized. I think it's useful to read things like that just to get a sense of what most people have found to be the best way. It's all very personal, but kind of standardize it that way. And the last thing is you are able to make that, the kind of the beauty of R is that it's open source. And so that means you can make your own packages. If you have a lot of functions that you find yourself using over and over again, you should make a package that contains those functions. And it's actually not that hard. It's pretty simple, thanks to some new packages, meta packages, I guess. So there's some links here if you want to learn all about that. But that is some advanced R stuff if you want to get there. But that's all I have. I think thanks for sticking around for finals week, and hopefully, yeah, let me know if you have finals questions or anything. Hopefully it was useful.
Thank you so much, Jessica.
Yeah.